I'm Matt Cannon from the chemistry department at Stanford, and I'm happy to moderate this morning's technical session on the second day of the GCEP conference on electrocatalysis for renewable fuels. I took the liberty of slightly modifying the title so Paul wouldn't feel left out. I'm going to basically give you a very brief overview of the field and some of the challenges in the next 4.5 minutes, and then I'll turn it over to our main speakers who will dive into a couple of different technical topics. So I think the overall goal and really the appeal of electrocatalysis for renewable fuel synthesis is captured on this cartoon taken from a very recent review, which basically shows you a flow diagram of the inputs for making fuels in a renewable manner using synthetic devices. So the inputs are CO2 and water. You could imagine getting CO2 from a point source or perhaps capture from air. And then the energy source, of course, is sunlight. And then in this gray box here are basically all the tasks that need to be accomplished to convert CO2 and water and energy into an energy-dense, desirable fuel. There are many different strategies for doing that. So basically, you can take photovoltaics to convert sunlight into electricity and then use that to power electrochemical devices which convert that electric potential energy into fuels. So the direct CO2 reduction, that means putting CO2 into an electrolyzer and getting a desirable fuel out. This is in the future. Alternatively, you can do water electrolysis or perhaps take CO2 to CO and then do conventional catalysis with syngas, CO and hydrogen, to elaborate those molecules onto fuel. So very briefly, if you think about the ways of taking renewable electricity and producing hydrogen, there's sort of a spectrum of technological possibilities. On the left here is conventional photovoltaics coupled to electrolyzers. So the purple here is a photovoltaic element, and then you have electrodes that produce oxygen. And hydrogen, you have some ion transport in the cell. You can then imagine integrating these components to various degrees, moving toward the right here, all the way over to the far right here, where you have basically an integrated photoactive component that absorbs light, generates charge separation, and promotes a catalytic reaction. And that's then coupled to ion transport and the complementary reaction at the other electrode. That's called a photoelectrode. And so the integrated device is called a photoelectrochemical cell. And if you think about what's possible today, if I just want to say I'm going to put solar energy in and get hydrogen out, you could take a available photovoltaic, couple that to commercially available electrolyzers. And these are actually very conservative numbers for what you could do in terms of overall efficiency of sunlight to hydrogen. If you take very old electrolysis technology, alkaline electrolysis, couple that to a fairly modest 15% efficient solar cell, you can get something on the order of 10% solar to hydrogen efficiency. If you use newer proton exchange membrane electrolysis, this is actually a pretty conservative estimate for the efficiency of that. You can get 8 to 10% efficiency there. And then the idea of photoelectrochemical cells is to integrate that and save cost by reducing the number of components. And you can get up to 12 and actually a little bit higher efficiency light to fuel conversion with photoelectrochemical cells, but none of these are established technologies. These are all laboratory numbers. So this is just a progression. In recent years, there's been an explosion of interest in this area. This is solar to hydrogen efficiency for photoelectrochemical cells. And you can see there's been a lot of growth, but there's huge issues with stability and the long-term performance and the cost of these integrated devices. And we'll hear more about that today. So that's water splitting chemistry. You have water oxidation at the anode, proton reduction at the cathode. If you think about CO2 electrolysis, it's the same anodic reaction, but then at the cathode, you're trying to activate CO2 instead of just dumping electrons into protons to make hydrogen. So you can imagine taking CO2 to CO, and then taking CO on further to hydrocarbon products or liquid fuels such as ethanol and propanol. There are electrode materials that are capable of doing this. By and large, they're not efficient enough to really be incorporated into devices yet. So unlike water electrolysis, there are no commercial CO2 electrolytic devices. So our speakers today are going to be talking about issues in catalysis and photocatalysis. So Haotian Wang will speak first about catalysts for water splitting chemistry. Paul McIntyre then will talk about photoelectrode strategies for protecting photoactive elements and integrating them with catalysts so that they can carry out the light absorption and catalysis. And then Jens Norskov will talk about theoretical descriptions of CO2 and CO reduction on various metal surfaces to try to get a fundamental understanding of that complicated chemistry. So with that, I'll turn it over to our first speaker, Haotian Wang. He's a graduate student in the Applied Physics Department here at Stanford. I think he's close to finishing his PhD studies. He's been working with Yi Sui in the Material Science Department. Yi's perhaps most famous for his battery work, but in the past few years, they've been looking a lot at electrocatalysis and in fact taking some battery materials and modifying them electronically and structurally to convert them into electrocatalysts. And so Haotian is going to tell us about some of that work today. Thanks. That's the pointer, and then that's it.
Thank you. Thanks so much for Professor Cannon's very nice introduction. It's my greatest honor to, on behalf of my advisor, Professor Yi Sui, to have this chance to give the presentation in the GCEP 2015 symposium here. I think my slides is coming out soon.
Yeah, give me a second.
So actually, as people may know, that Professor Yi Sui is very famous in battery, lithium-ion battery research, but we're trying to borrow some of the ideas and technologies from the battery community, but applying in the electrocatalysis. Okay, it comes out. So the topic of my talk today is the electrochemical tuning as a new method to search for active catalysts. So let me first off show you a picture of a city that is heavily polluted by air PM 2.5. So, and a recent investigation actually showed us that the air pollution actually comes from the fossil fuel consumptions, that's such as the coal-fired powered plant, as well as the exhaust from the automobiles we use, and also the personal use of coals for burning, for heating, and so on. But all of these fossil fuel consumptions actually contribute an even more serious global issue, that is the CO2 emission. As we know that with the continuous increase of the concentration of carbon dioxide in our atmosphere, the average global temperature is actually increasing by much over the years. If this case continues, as we know that, there will bring us a lot of unpredictable issues to our ecosystem and environment. So actually, we need a very fast, clean energy revolution. We need to produce clean, renewable, sustainable, as well as zero-emission energy for us to replace those fossil fuels. And actually, hydrogen comes out as a very wise choice because it has a very abundant source, which is coming from the water by water splitting electrocatalysis. And also the products, after we use the hydrogen, is also the water, which is pretty clean. And also hydrogen has the highest gravimetric energy density. And if we look deeper into the full reaction of water splitting by electrocatalysis, we can see there are actually two half reactions. One is the hydrogen evolution reaction, that you reduce the proton into hydrogen. And the other is the oxygen evolution, that you oxidize water into oxygen. And actually, we have very good catalysts that is made of the noble metals, such as the platinum and iridium platinum, which can drive the hydrogen evolution at even zero over potential. But for oxygen evolution reaction, we actually have iridium oxide, ruthenium oxide, which is very efficient catalyst, but still requires several hundred millivolts to over potential to drive the oxygen evolution. So if you add in the two starting point together, and it can easily give you an efficiency of electricity conversion to hydrogen energy that it goes to more than 80%, which is really high. But as we know that those noble metals are very scarce and expensive, so the best way for us is to develop a very low cost and very earth abundant materials with very high electrocatalytic activity to replace those noble metals. So over the years, our strategy is trying to developing different tuning methods to tune the layered materials, such as using the structure tuning, chemical potential tuning, as well as morphology tuning, to try to tune the material properties as well as their electrocatalytic activities and search for very high active catalysts. And the reason why we are focused on layered material is because of their flexible tunability in their material properties. Due to their very unique crystal structure, that is, they have atomic layers that is covalently very strong bonding within the atomic layer, but those layers stacking along the z direction with very weak van der Waals interaction. So this high bonding anisotropy gives us a lot of opportunities, such as reducing the dimension within different atomic orientation, and also you can intercalate a lot of gas ions between the van der Waals gap. You can do gating, you can do high pressure, a lot of different technologies for us to tune the material properties and also examine their catalytic activities. So molybdenum disulfide as a very famous layered material, outstanding layered material, which has been realized that the edge, in 2005, Professor E.S. Noskov actually predict that the edge size of molybdenum disulfide, not on the tera side, but on the edge side, that is actually very catalytic active for hydrogen evolution reaction. As we can see from the phase diagram, the free energy diagram, that the molybdenum sulfide has actually very low free energy that is very close to zero, which is similar to platinum, which means that you have a bonding. On the edge side, you have a bonding which bonds the hydrogen, not too strong and not too weak. That means that if you bond the hydrogen too strong, you have a problem that when you hydrogen release, this step will become rate limiting. But if you bind the hydrogen too weak, there will be a very slow step for the electrons to pump into these hydrogens. So the best catalyst is you just bind the species not too strong and not too weak. So, and Professor Tom Hermel, when he was a postdoctor, he actually developed this experimental demonstration of the active edge side, that he grows the molybdenum disulfide nanoplates and tests the catalytic activity. And this activity correlates, actually has a linear scale with the length of the edge, but not with the surface area of the plates, which strongly demonstrates that it is actually the edge side that plays the key role in the hydrogen evolution reaction. So we actually think about the atomic structure of molybdenum disulfide and think what is the best structure for us to do. As a lot of research coming from the discovery of the graphene at the 2D material, that people just thinning down the 2D layered material through Z direction to obtain single atomic layer molybdenum disulfide to do their transport measurement or something. But in our case, we actually want to expose more and more edge sites. So we are trying to reduce the dimensions through the XY direction. So our ideal structure is that if we can synthesize a molybdenum disulfide layered structure, but with their layers vertically standing on the substrate, this will help us to expose 100% more all the active sites on the surface. And the way we want to achieve that is through the chemical vapor deposition through high temperature. As we can see that we have a moly thin film deposit on the substrate, and we evaporate sulfur and react with moly at a hot zone within very short time. And as we can see from the TEM image, the electron beam is actually perpendicular to the screen. You can see a lot of gaps, that is van der Waals gaps, facing to us, that demonstrate that the structure is actually layers vertically standing on the substrate. And the reason this structure is actually, as people may think about the surface energy of this edge site is very high, and this structure might not be the thermodynamic stable phase for us to obtain. But the reason why we can drive this reaction happen is because at this high temperature synthesis, the moly and sulfur react so fast. The rate limiting step becomes the sulfur vapor diffusion limit. So with layers vertically standing, open the van der Waals gap, we can have a very fast diffusion of the sulfur gases through the layers, and this becomes a preferential orientation of the layers. And we also test the hydrogen evolution catalytic activity of this kind of thin films, and we can see there is still over 200 millivolts over potential to drive this reaction. And if we look deeper into the edge sites, we actually realize that there are two types of edge sites. One is the moly edge site, that is the actually active sites for hydrogen evolution. And the other site is the sulfur edge site. And with the help from Professor Jens Noskov, that from the theoretical simulation, we realized that the sulfur edge site is actually bound the hydrogen too strong, which will not be active for the hydrogen evolution reaction. So the way we want to activate this half sulfur sites is if we can dope this edge site with transition metals, including nickel, iron, cobalt, we can actually see that the free energy decrease very much and activate the half part of the edge sites. And a very easy way for us to achieve that is we just evaporate additional very thin layer of transition metal on top of moly and do the sulfurization at the same time. You can see that the concentration of these transition metals will focus on the very top surface, ensuring that we have the most of the sulfur edge site can be doped with these transition metals. And as we can see that the catalytic activity is indeed doubled after the doping process. And if we look deeper into the electronic structure of the molybdenum disulfide, how can we improve this catalytic activity further? As we can see that this unique crystal structure allows us to intercalate a lot of gas ions. Those gas ions, for example, alkaline metals, they can contribute a lot of electrons into the layered structure. And this charge transfer will significantly tune your chemical potential, your electronic structure by much. And with the well control of this electronic structure, we can actually improve our catalytic activity within a controlled manner. So for a very intuitive understanding, that is, for every chemical reaction, we have the chemical potential. And if we intercalate lithium ions into the molybdenum disulfide, we may be able to bring down the chemical potential of the molybdenum disulfide, and which may be getting more closer to the hydrogen evolution reaction and reduce the over potential by much. So a very easy way for us to do that is to construct a lithium-ion battery and intercalate lithium ions between the van der Waals gaps. And this lithiation plateau represent a very good, well-defined phase transition from the 2H semiconducting phase to the 1T metallic phase. And also, there might be a lot of changes during the lithiation process, and we stop the lithiation voltage from 1.8, 1.5, and 1.2, and 1.1. We stop at each potential and take the sample out to examine what happened to these samples. As we can see that the pristine molybdenum sulfide until 1.8 and 1.5, there's really no change to the structures of the thin film. But if it goes to the phase transition regime, 1.2 volts and 1.1 volts, you can see these layers are partially exfoliated with a much larger layer spacing. And also the electronic structure changes by lot. So when you have a 1.8 and 1.5 volts lithiation voltage, you can see the XPS, the oxidation state of moly gradually shift towards a lower binding energy, which represent that oxidation state of moly is reduced. But when you have the phase transition happens, there are one new peak comes out, that is the one representing the 1T phase that gradually increase the ratio compared with the semiconducting phase. And also the Raman spectroscopy shows the coming of the new peak. And also we finally end up with testing the hydrogen evolution catalytic activity by this electrochemically tuned molysulfide thin film. As we can see that with a lower and lower lithium voltage, we can get a higher and higher HER activity. And also we can see that the Tafel slope is actually flipped from 120 all the way to 40, which is very low Tafel slope at that time. And this successful demonstration of electrochemical tuning to improve the catalytic activity strongly drive us to see if we can also do a similar work in the other half reaction of water splitting, that is oxygen evolution reaction. But instead of bringing down the chemical potential of your catalyst, we're trying to bring it up because of the oxygen evolution reaction is much higher voltage than the hydrogen evolution. And this is correlates very well with Professor Cannon's previous work when he was a postdoctor, that the cobalt transition metal, the oxidation state of the transition metal, if you have a higher transition oxidation state, you might get a very good OER catalytic activity. So the first example we want to demo is the lithium cobalt oxide, which is the traditional cathode, the positive electrode material in lithium-ion batteries. It is also a layered structure with lithium ion sandwiched by cobalt oxygen atom slabs. And the way we want to do that is trying to extract a partial lithium out and bringing up the oxidation state of cobalt. As we can see that the average oxidation state of cobalt here is +3. And if you extract 0.5, half of the lithium out, you can achieve a 3.5 oxidation state of cobalt, significantly elevate its oxidation state. As we can see from the testing result, when you extract the half lithium out, the oxygen evolution reaction catalytic activity is strongly improved. As we can see that the black curve is the pristine lithium cobalt oxide. You have an onset potential around 1.6 volts. But when you do the lithium electrochemical tuning process, it's reduced to nearly 1.5 volts. And also, if we incorporate other transition metals into the lithium cobalt oxide material, such as the lithium nickel oxide, lithium nickel iron oxide, actually we can see all of these materials after the extraction process, the catalytic activity is significantly improved. And the hero comes from the three-element combination, which you can have even better catalytic activity than the noble metal of iridium. That is the benchmark of catalyst of the oxygen evolution. And finally, we come to the question, if we want to build up a system that is for practical water splitting, then you need to consider combining these hydrogen evolution and oxygen evolution catalysts together. As we can see that a lot of the research is in the community, they have been doing different catalysts in different pH ranges. For example, the HER, a lot of have been done in acidic solution, but OER in alkaline solution. So there makes us a problem that how can we combine these two catalysts together in a real device? So the best way for me to think is if I can develop only one single catalyst that can drive both reactions, that we call it bifunctional catalyst, then we can stable it in the same pH when there is no pH mismatch. And also at the same time, I reduce half of the fabrication cost of the system. And the candidate I want to choose is transition metal oxide. That has a very wide stable electrochemical window covering the whole water splitting potential window. So the way we want to increase the catalytic activity of transition metal oxide is also inspired from the lithium-ion battery studies in our group. So transition metal oxide is also a traditional lithium-ion anode materials. And the studies in this community, they found that after several cyclings of lithium charge and discharge, that is the lithium goes into the transition metal oxide and comes out. Actually, the structure of the particle will be significantly changed after several cycles. As we can see that from the TM image that you start with a monocrystalline particle, but after one or two cycles, it ends up with ultra small nanoparticles, but strongly connected with each other, significantly increase the surface area and the catalytic activities. So we test different transition metals, cobalt oxide, nickel oxide, iron oxide. After 2 cycles of the charging-discharging process, we find that the oxygen evolution, all of them improves a lot. And the best one comes from the mixer, the nickel iron oxide. As we can see, the blue curve is the benchmark irradiant carbon. And after tuning, we can see the performance of the OER after tuning process is much better than the irradiant. And interestingly, we also realized that the hydrogen evolution reaction for the same material, nickel iron oxide, after tuning, is also significantly improved. As we can see, the pristine has more than 300 over potential, but it shifts up to 100 over potential, and which goes very close to platinum. So we can successfully combine these 2 catalysts, the same catalyst, together to drive the full water splitting reaction. As we can see that we hold a 10 milliamp per centimeter square current and test the voltage need to drive this current. As we can see that we combine the iridium, which is OER catalyst, and platinum HER catalyst together. As we can see that with the time continues, the voltage required to drive the 10 milliamp is increased continuously. But for our bifunctional single catalyst, the voltage is stabilized. And when you increase a little bit of the loading, you can see that you can achieve this 10 milliamp at only 1.51 volts for 200 hours without any degradation. This will give us a very high efficiency that goes to 82% of the electricity conversion to the hydrogen. That is pretty high. And also the stability is really good. So let me show you a video that compares my catalyst with the iridium and platinum. So I drive both the 2 systems and under 200 milliamp, which is very high current density. You can see my bifunction catalyst has very tiny bubbles coming out from the electrode. But if you convert them into the platinum and iridium, you can see a lot of big bubbles covering the surface, blocking a lot of active sites. So in the end, during the past 1 or 2 years, we have been developing a lot of different tuning processes to increase the catalytic activity and replace those noble metals for water splitting reactions. And our future plan is also to apply these successful technologies in other different electrocatalysis, as well as we will have a strong collaboration with Professor Wang's group with their technology in synthesizing layered oxides and their good characterization abilities. So in the end, I want to thank the continuous support from GCEP as well as the Stanford Interdisciplinary Graduate Fellowship. With that, I would like to take any questions you have. Thank you.
So we have time for a few questions for Haotian. Maybe I'll start with one question. So with the lithium cobaltates, when you delithiate them, I guess another way of looking at it is that you're breaking that extended lattice up into smaller clusters, and then the oxidation state of the cobalt is set by the potential of the electrode. So can you distinguish that from basically trying to set the electronic properties of the catalyst prior to applying the potential for water oxidation? I mean, do you know, for example, as a function of delithiation, is the steady state oxidation state of the cobalt any different during the water oxidation process?
That is a very good question. So actually, let me explain that a little bit in details what the process happened. So the first thing we want to do is not in it's in organic electrolyte that is used in the lithium battery system that you extract lithium out, and this lithium 0.5 cobalt oxide is the product we want to use.
Right.
And this material is actually very stable when you scan your voltage in the aqueous solution for oxygen evolution. At that time, that might be right. So you scan the voltage from, for example, 1.2 volts all the way to 1.6 volts. You drive the oxygen evolution. The surface might be changed, but the bulk system is not changed.
Okay, so you do have to break up those extended lattices then into, is that the notion, into small pieces?
Yeah, it's very small particles.
To get that to
yeah.
go. Okay. Yes, Al.
So in electrocatalysis, it's mostly the surface that's important, unless you have a very porous film or something. And so although people like to correlate bulk properties with things, it's really the surface that makes all the difference. So if you're interpolating lithium, that's more of a bulk property change. Is it the electronic effect that affects the surface that you think makes it a better catalyst, or what's your feeling?
So yes. So actually, as you can see that when you interpolate lithium inside, the electronic structure of the whole system is actually changed. You drive a lot of electrons. You higher the Fermi level, the chemical potential of a molybdenum disulfide, for example. It actually has a phase transition from the semiconducting phase to a metallic phase. So the whole system is changed. The surface is changed. The bulk material is also changed.
Yes.
How long have you been able to have it received output? 80 years?
Sorry?
The lifetime of the catalyst. How long have you pushed it to several days or?
So the last one I showed you is the 200 hours without any degradation. That correlates maybe less than 10 days, but more than 1 week. But we can actually, the stability of a catalyst, when you test it in the lab, is also limited by your electrode you use. So there is one issue that you need to develop a very robust electrode to hold those catalysts.
You mean the current collector?
Yes, current collector, yeah.
Okay, was there another question over here? Yeah.
Son, the video that you showed with the two catalysts back to back in the bubbles was really fascinating. Could you comment on two things? One, to what extent did you characterize the morphology of the two, especially your kind of iridium and platinum reference? And then do you think, how much of a role does bubble nucleation play in the difference in overpotential?
So yeah, this is a very good question. So the difference between the catalyst I developed and the reference, the iridium and the platinum catalyst, is my catalyst is directly synthesized on the current collector. But the commercialized platinum, iridium, they have a lot of carbon additive inside. As people may know that carbon is very hydrophobic. It traps a lot of bubbles. That is a very, and also this kind of catalyst loaded on the current collector will have, you need to have some binders to bind strongly on the substrate. But under a very long term of operation, the lifetime is not as strong as you directly synthesize your catalyst on the substrate. Yeah, and also you have a bubble release. So the bubble is an issue that you have problem when you drive a very large current. But for a simple measurement, for example, it goes to 10 or 50 milliamp, that is not a big problem. There is no big change if you have the bubbles or not, yeah.
Okay, so that's just about it for our time. So please join me in thanking Haotian for a great talk.
Thank you.